And therefore, we would expect for them to have a maximum permeability or conductivity or transmissibility in one direction, my 2.5 mile versus 660 feet case. So here's an aspect ratio of 20-fold. And I've got news for you. That's not an unusual aspect ratio. 20-fold has a very specific signature. And that's it. This is, if you did this calculation with a classic finite difference simulator, unless you were using extremely small grid sizes, you couldn't model this. This is one of the beauties of using finite element, because you wind up with a bunch of cross derivatives and a bunch of stuff that only grad students like, and mostly only the pilot higher deepers like. I am one, so I can talk like that. You know what an expert is, don't you? You know what an expert is? Expert has been drip under pressure. Never mind. Bad joke. Backwards awake. Front row has to stay awake because they got to dodge all the sloppers going their direction. The back row has to stay awake because they have to put up with my bad jokes. Anyway, the model was given an aspect ratio of 20-fold. 20-fold aspect ratio means that that ellipse is 1 unit wide by 20 units long. That thing's pretty skinny. It's beginning to kind of sort of look an awful lot like linear flow. Linear flow is nothing but the case where the anisotropy is so severe that one axis essentially goes away. It is the limit, if you please, of ellipsoidal or anisotropic behavior. Yeah?
This is a little off topic, I guess, but have you used any type of data to prove your actual frac length, like pumping tracers or anything like that?
Oh, now you're in the swamp. How do I answer this appropriately? Yes, and the answer is no. Hang on to that. Don't let me get away from that one. The reason is, and I'm going to try to bring you back. Most of you are probably familiar with, you may have read literature by a guy by the name of Bob Maree. Bob's a brilliant man. I mean, he's wild. I was his advisor. And we developed the basic theory that became his program that he calls Gopher. Gopher is one of the preeminent fracture design models. I mean, it is an excellent model. But it is based on the assumption that I'm going to tie this to you for what you're asking, I think. All of the fracture design models are based on the assumption, that the fracture is symmetric, constant height, same thickness, all the assumptions, and two wings that are equal length. Unfortunately, I got to do a bunch of work with Norm Warpinski and Pinnacle in the microseismic. And the minute you look at a microseismic picture of the events that represent the so-called stimulated reservoir volume, you're confronted by the fact this idea of a two-wing symmetric fracture is nonsense. Okay? Well, all of a sudden, all of that body of theory just took a serious hit. Well, it didn't. Using those concepts are appropriate metrics as long as you only view them as metrics. Okay? It's a way to talk about good, better, and best, and worst. But in terms of a physical phenomenon, it doesn't occur. Right? And there's some really good results out about a test site. In fact, I can show you some pictures if you want to go there after this, that really do raise that point, that this idea, the concept of fracture length is simply, okay, if this complex of fractures, wherever they went, were a single fracture, it would look as if it were so long. Does that make sense?
Yeah. Another question.
Please.
Frac length, are you talking about total frac length or effective frac length?
Well, back to the comment about the microseismic. I have chosen to use the word apparent to even avoid that debate. The calculation itself is, in this case, in this situation, because I've got a simulator that used a single wing symmetric fracture. All right? So that the model that I'm using, the theoretical model, had the single wing symmetric, all the niceties. So that calculation is the created, the effective, propped, all of those things, simply because of the way I created the simulator. In the real world, the created length is probably 10 to 100-fold greater than the propped length. Okay? So the product length might literally be 1/100th of that which fluid opened up. It depends on pad volume, depends on fluid viscosity, depends on pumping rate, a lot of different variables in how much creative length you have. Then the issue is how far did the proppant go? That's a function of breaker, that's a function of viscosity, that's a function of rate, a bunch of other variables. Then comes the question of the effective. Well, the effective length is that which is able to deliver fluid back to the wellbore. All right? And the sad news is when you start wrestling with the idea, I've got a whole lecture on that issue we won't have time to get to. But very likely, when you take into account the mobility ratio concept, you're stuck with the fact that you might be lucky to have the effective length be 1/10 of the propped length, simply because the mobility ratio is so adverse that if you pull the well too hard, you combed the gas and the oil in right at the wellbore, and the rest of that fracture is utterly useless. Okay, so then we go to this issue of geometry, and it may, all of those ideas are based on this idea of a symmetric, Now I look at the microseismic and I see that right near the wellbore there were 1,000 events. And so I'm stuck with this idea that tortuosity is a major issue, and I'm going to try to talk about that tortuosity as if it were an effective. And so that's why I went another step and I said, I want to talk about it as an apparent length. It's as if it were symmetric and so on and so on. Okay? Does that make sense? So I'm really stuck with having to come up with some words to describe what inside here matches with what the worldview is. That's where I came to. Okay? Thank you. Right on. All right, so here's this anisotropic system. In the limit, it becomes the linear flow system. And look, when I did the calculations, and this is all published in Carslon Jaeger, not that you want to go read Carslon Jaeger, because Carslon Jaeger's 560 pages of heavy stuff. But this whole discussion occurred on page 32. It wasn't page 750 or something way far back in the book. It was one of the very first concepts that they introduced. And interestingly enough, we in our well testing, we probably don't spend much time in this neighborhood with the hairy math of it, but the original concepts of superposition or convolution were introduced by Duhamel. Duhamel introduced these ideas of anisotropy in crystallography back in the early 1800s, 150 years ago. So this is not a new concept. The math is not new. It's just that it hasn't migrated over to the petroleum literature for some reason. Anyway, they point out that this is quite manageable, and the computations are relatively straightforward, and the physics of the system is well described. The other case, pseudo-steady state or boundary dominated or whatever magic word, obviously that's part of the question. The same matching process, except now I'm looking, if you look at the literature, this is another piece of our discussion, you've dealt with the idea of Horner equivalent time, cumulative production divided by the ending rate. When you did your Horner plot, you had to calculate T sub P plus delta T over delta T, or the two turned it over. I mean, there's lots of ways to, same idea. But you had to talk about T sub P, the producing time. Well, that basically is this idea of the Horner equivalent time, the Q over Q. If you go read Bob Wattenbarger's work, or, drawing a blank, some stuff that Mike Conway has done, there's another one. Well, Tom Blasingham's got some articles about it. Anyway, if you do what is referred to as mass balance time, mass balance time is exactly this idea. It's the same basic process. Fancier words, but basically you're taking the Q over Q and plotting that against this efficiency term. The slope of that line is proportional to pore volume. That's very cool, because all of a sudden I've got a way to look at the early time and the late time. All right? And the model does a credible job again. Drained area is 167 acres. Now, given our conversation a minute ago about a 14,000 foot thick hydrocarbon section, what does drained area mean? Now you say, well, that's not well testing. That's reservoir engineering. No, it's well testing. Because in well testing, we're looking for the event, and usually the well tests are of such short duration, if I've got a buildup that's on the boundary, I've got some other issues. What does that mean? What does that physics mean? What is the physical consequence of talking about a drained area? So what? Who gives a rip? Well, I give a rip, or I wouldn't have brought it up. The rip is, this drained area is predicated on an assumption of thickness which contributes. Before we take a break, we've got one more slide, a couple more slides here, but we'll get there. Let's wait. I want to deal with this. Given the understanding about anisotropy of the system and the understanding about heterogeneity of the system, how likely is it that two wells have the same reservoir quality? Never happens. Never, ever happens. Just don't happen. Hey, Leroy, you ain't going to do it that way. Hey, you're right, it is not. That's off the table. Now, if I were so arrogant as to say, well A produced 10,000 barrels in the first month, and well B produced 5,000 barrels in the first month, and well C produced 20,000 barrels in the first month, I have done the classic 1 month cumulative production, initial production comparison, and this well C over here just is awesome. Those guys get a bonus. Should they? Go back and think about your well testing. Should they? Yes, it produced a lot of oil. Yes, it produced 4 times what well B did. Sorry. No, it's not. But anyway, they chose to come back and sit up here. What do you say? Dangerous place. Whoever thought well testing would be dangerous, huh? Never mind, don't go there. 20,000, 5,000, 10,000. Should the guys that got 20,000 barrels in this well be receiving a bonus? Yes or no? Huh? Defend your statement. And? But now let's get into the why. He's right. He's absolutely right. Dead on. Because I may have destroyed the well because of the way I changed the pressures, or because of the reservoir quality, or because of the drained area, the pore volume that could contribute. The guys that only produced 5,000 barrels in that first month actually may be the ones who deserve the reward, simply because they had such a terrible KH, and they had such a terrible initial pressure, and they were operating with no compressor, no artificial lift, so they had a very high back pressure. All right? So it is not true. It is just categorically not true that comparing volumes only is a metric that is a fair test of a good well versus a bad one. And so that introduces this idea of normalization. Darcy's law says, and this is good old Darcy himself, 1856, Q rho, the pounds of stuff produced, oh, those darn chem engineers, dang it, wish we could visit it and all. Q rho, pounds of stuff, is proportional to a transmissibility term that talks about the area, like as if in the frac job. The transmissibility and the drawdown. So if I have, when I compare these 3 cases, notice I carefully step back. Important. When I compare these 3 cases to decide who deserves the bonus, I need to look at the quality of the reservoir, the size of the stimulation, and the severity of the drawdown. And until I normalize the data to take those into account, I'm not making a fair comparison. Now, why is that important? Well, I would assert to you that from well testing, I can get a good assessment of that reservoir quality. I would assert to you that during that well testing, I'm probably, at least implicitly, considering the drawdown. And certainly when I look at the completion, I'm thinking about how efficient the well was completed, how efficiently the well was completed. So, it is entirely conceivable that when I normalize the data, this 5,000 barrel a day guy actually is by far the best well. Not because it didn't have the highest revenue, because it didn't, obviously. But in terms of an engineering question, it was best. See my point? All right. So, all I want to do, and then you've got this page, and basically this is simply trying to get to your attention that when a company brags it, one of my former clients, this almost became a lawsuit, I dodged the bullet. They were making representations to their investor group about how good their wells were. And that's where this came out to be a huge issue for them, because what we showed it was, and obviously, I'm not kidding, I dare say I have been fired more times than all of you will have changed jobs in your career. It's just the way it is. And I think that's important, because many consultants will try to give the client the answer they want. And I don't think that's right. I have a really fundamental ethical problem with that. I'm sorry you don't like my answer, but this is the answer I got. Here's how I got it, and I'm going to stand by it. And I think that's one of the things that we as engineers have to do. Because I got to tell you, there's some folks in the business right now whose ethics just really bother me a lot. And one of the things, if you look at SPE, the Society of Petroleum Engineers has as a specific overture this issue of engineering ethics. And I think it is so important. It's scary. I got to tell you, it's scary as all get out. Because tomorrow morning you may be advised that it's time for you to work someplace else because management didn't like your answer. I'm not losing weight very effectively. And I have been offered to not talk to them again on a regular basis. I'm okay with that. My clients know that they don't have to like my answers. But I just think it is so important for them to know, I don't care whether you like my answer or not, this is what I saw and here's how I saw it. And I would challenge you, because you're going to be confronted with it more than I ever have been. The companies are going to be putting huge amounts of pressure on you to make decisions that are beneficial to them, not necessarily good for the engineering and not necessarily ethically. And that's an important idea. So, when I come back here, I want to have a method that lets me make a good decision that takes into account all of the engineering factors that I know pertain. All right? So this is a way to do that. Now, all that stuff. We're going to wrestle with you and we'll take a break. I have alluded to the idea that pore volume is a function of thickness. I have alluded to the idea that reservoir quality is a function of thickness. I will allude to the idea that stimulation effectiveness is a function of thickness. Have you ever heard of anybody, and of course none of my frac jobs ever had this problem, have you ever heard of anybody talk about a frac going out of zone? Well, that's the big issue that happened up in Susquehanna County, Pennsylvania, that caused all this stink about hydraulic fracturing being so harmful. The company didn't do a good job of cementing the well, and as a consequence, the fracture went outside the cement sheath, went up whole, and went to the surface. Frac height, that wasn't actually frac height growth, that was a crappy cement job, just like Macondo. But the bottom line is, fracture height growth is an issue. Sometimes you design to try to cause it, sometimes you try to design to prevent it. But it is a variable. So, I just introduced the idea, and this is an important idea, I think. There are three possible thicknesses that affect the behavior of the well. The thickness associated with the stimulation. How tall did the fracture grow? How much of that height is propped open? And how much of that height has hydrocarbon flow through it? All right, so that's thickness number one. Thickness number two. That thickness through which flow occurs in the reservoir. Ugh. Wrestling point. Is that thickness measurable with a log? Remember our conversation a while ago? Yes or no? Well, it is estimatable, but it is not directly measurable. because there is no physics that says that just because the porosity crossover of the neutron densities predicts the actual thickness through which flow is occurring. So number two, thickness through which flow. Number three, the thickness which provides energy to the system. All right? So there are three thicknesses that we've got to wrestle with that affect the behavior of our system. Now, why is that important? Well, it's important from here. When I first put the well in production, that very earliest production is associated with the stimulation. Therefore, the thickness associated with the stimulation controls behavior. As the well ages, oh boy, as the well ages, that thickness is no longer so important, and now the thickness through which flow is occurring becomes important. You see how that's working? As the well continues to age, and now begins to get into the scenario that I've got a fairly large volume of rock that has pressure contact in it, the pressure has dropped, I am now confronted by the thickness from which energy comes. The geologists like to refer to that as the percolation thickness. To us, it's just simply that thickness that is controlling the pore volume. So all of a sudden, I am confronted with the fact that I do not have a simple, nice, really cool, easy to deal with, the thickness is 12 and a half feet. Yesterday it was 12 and a half feet, today it's 27 and a half feet, and tomorrow it might be 14,000 feet. So we've got to start wrestling with the idea that the physics of this system is transient in every respect. All right? Whew. All of you are in the process, have had, or will have well testing. And you've already heard that I have a certain degree of cynicism, for which I apologize, because I taught it for 14 years. I taught both the undergraduate and the graduate class in well testing, so it was common that I would teach it twice a year. And I reached the point that I had taught it so much that I didn't have to use notes. I could do the derivation from memory, which has to tell you something really scary about this guy standing in front of the room, I dare say. Anybody that can do the derivation from memory probably is anisotropic, heterogeneous, abnormal, just a whole long, don't talk to my son. Anyway, that's just the way it is. So, with that disclaimer, let's go here. Why is it important to deal with the theory? Well, one of the reasons is very simple, and I brought this issue to you at the outset. The traditional belief has been that it was not possible to use this kind of data for the purpose to which I'm going to put it. And therefore, I have to see that the theory supports what I'm about to do. It's that simple. But there's some other pieces to the story as well. But that's really where the process starts, is this confrontation between what Grafton's doing and what the traditional belief has been. So, I hope one of the ideas that's beginning to wrestle its way into your head is this idea that a well's history is a path. That's why I ended my conversation a minute ago with you about the idea that thickness changes. That thickness which controls a well's behavior changes as the well ages. Right? I dare say that question had not been raised to you before. 10 years ago, I wasn't smart enough to raise it. I hadn't thought this process through. That said, I then am confronted by the fact, and this graph, it's a crappy graph, but my intent of it is to try to get you to wrestle with the idea that the way a well ages is strongly a function of its prior history. And so that's really what this picture is trying to engage you in. What I do during the flowback after the frac job will affect the EUR. You say, that's dumb. Of course it would. Yeah, unfortunately, this is a point where this idea of the value of money comes in. Have you seen any press releases where companies have been bragging about producing 35 million a day or 1,200 barrels a day? Seen any of those? Well, I've seen quite a few of those. Comment was made a while ago about that point. Time value of money is what this is really all about. If you believe the time value of money is infinite, then you don't care what happens tomorrow. All you care about is what happens today. If your time value of money is 3, 5, 10%, then you care a lot about what happens tomorrow and next year and 10 years out. So it really, in a very different sort of way to think about it, net present value, which you either have or soon will be confronted by, the concept of net present value is really the driver in this whole discussion. So no, this is well testing. We're talking about that straight line equation. No, you're not. No, you're not. That is simply some of you will spend your time, and if you get a chance, there's a lady by the name of Ellen Cooper-Smith. She has a company called Decision Strategies in Houston. Ellen is probably in my opinion, one of the preeminent operations research people in the world, because that's what her specialty is doing operations research in the terms of risk management and net present value. Well, you start wrestling with, here's the governing equation. That's the equation that governs the behavior of our systems. But our task is to understand that in terms of making money within the framework of what we consider that money to be worth, the net present value. All right? Net present value, if you perceive the money is worth an infinite rate of return, that changes the net present value, and that changes how you manage that equation. And that's what operations research is all about. So, if I have a low net present value, or a low rate of return, I should say, then I'm very interested in when the well reaches the point of going into pseudo-steady state. If I have an infinite rate of return, 35 and up, 35% and up, there are some companies that use as their internal rate calculation 75%. They are doing business in such a setting that a year out, that money has no value whatsoever. It really doesn't. So, this really does, this graph, this way of thinking through the behavior of these systems is driven by what we think the time value of money is. If my goal is solely to generate a high initial production rate, high IPs, then what I just admitted to you is I'm using a very high rate of return. If my goal is to try to have the best possible 2-year production, I'm looking at a rate of return that maybe is in the order of 20%. If I'm telling you that I would like to have something that is going to last for 20 years, I'm telling you that my rate of return is something in the order of 5 to 10%. So all of these have that translation back to the value of money. And that's really what drives this. And that's why the conversation about normalization. So we're going to look at it in 4 pieces. We're going to think about the early time piece, the period of time when the acid job or the frac job dominate the behavior of the well. So that's this early piece. Then we're going to think about the middle time, the part where we did the stimulation, where we paid money to try to improve the connection between the reservoir and the wellbore. I'm going to repeat that. The early time is the period of time where we paid money to Halliburton, Baker Hughes, Schlumberger, Calfrac, whoever. We paid them some money to try to improve the connectivity between the wellbore and the reservoir. That's false. Wish you'd quit that crap. That's just frustrating. I know. That's why I did it. It's not about the connectivity between the wellbore and the reservoir. It's the connectivity between the wellbore and the natural fractures which connect to the reservoir. There is not a reservoir, and now I got to tell you, if you'd heard this lecture 20 years ago, you would have heard me stop and not contradict myself. I have become adamantly convinced, I have become passionately convinced, we have made a serious mistake in our understanding about reservoir systems. There is not a reservoir system in the world that does not have a natural fracture component to it. Now, it may be big or it may be small, but it is there. If it is there, then it is part of the system behavior And part of our decision then is how to make use of it. All right, sometimes we ignore it because it's not important. Sometimes it's everything. And I can tell you with absolute confidence, in the Marcellus, if you do not have a significant natural fracture component to the well's behavior, the well will not be economic. It's that simple. Well, that's a real game changer because all of a sudden, my goal is not necessarily to connect to the reservoir, it's to maintain a connection to the natural fracture system. All right? So, I'm confronted with the fact that this early time piece is that time looking at the behavior of the system at the time where I spent money to connect to the natural fracture system. Then comes a time when I look at the natural fracture system and its connection to the reservoir. Then, I'm now out into this middle time response. Then the reservoir's response. Then the transition once the pressure wave hits the side of my pond, and I'm going into pseudo-steady state. And then once I'm in fully dominated pseudo-steady state, or fully boundary dominated response. Okay, so I've got this path. I can influence the path. My task is to create a path that maximizes the value consistent with my perception of the net present value, or the value of money. Does that make sense? Did I just tell you a story right over your head? I hope not, because that has become my business model, my picture of how these systems behave. Play it again. The first response is the response